By 2025, 90% of new enterprise applications will be AI-powered and cloud-native, completely reshaping how we build software.
Wait, 90%? That seems impossible in just a year.
That's exactly why understanding this AI Kubernetes symbiosis is critical right now.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're diving into the symbiotic revolution, AI and cloud-native technologies transforming the digital landscape.
But first, let's cover today's top headlines.
There's a fascinating new development from Red Hat's developer team. They've connected AI to Istio through Kiali, and it's really pushing the boundaries of Kubernetes observability. According to their latest article, you can now have AI agents actually inspect your service mesh traffic flows in real time.
Hold on, that's pretty significant. So we're talking about AI that can understand and analyze the complex traffic patterns in Istio? How does that even work with Kiali?
They're using something called the Kubernetes MCP server as the bridge. Basically, Kiali, which is already the go-to management console for Istio, now exposes its data in a way that AI agents can consume and interpret. Think of it as giving AI eyes into your service mesh.
That could be a game changer for troubleshooting. Instead of manually digging through traffic flows, you could just ask an AI what's going wrong.
Exactly. And speaking of observability evolution, AWS CloudWatch just made a huge leap. InfoQ reported that CloudWatch is transforming into a unified observability platform with Apache Iceberg support.
Wait, Apache Iceberg? That's typically for data lakes. What's AWS doing here?
They're solving the multi-account log consolidation problem. With Iceberg support, you can now query logs in place using standard SQL without moving them. No more copying logs between accounts or regions. Just query them where they live.
That sounds great for cost savings, but what about performance? Querying distributed logs across accounts could get slow.
That's where Iceberg's table format comes in. It's designed for exactly this kind of distributed querying at scale. AWS is essentially turning CloudWatch into a federated log analytics platform.
Both of these stories really show how observability is evolving beyond just collecting metrics and logs. We're seeing AI integration and distributed architectures becoming the new normal.
Absolutely. Platform teams are getting more sophisticated tools to manage increasingly complex infrastructures. That covers today's headlines. Now let's get into our main story. So let's talk about something that's fundamentally reshaping how we think about platform engineering, this convergence of AI and cloud-native technologies. We're seeing this symbiotic relationship emerge, where AI isn't just another workload running on Kubernetes, but it's actually transforming how we build and operate cloud-native platforms themselves.
Yeah, I've been noticing this shift in my own work. Just last week, we had a situation where our traditional auto-scaling rules completely failed to handle an AI inference workload. The resource patterns were so different from what we'd designed for.
That's exactly the kind of challenge that highlights this transformation. The traditional cloud-native playbook, stateless microservices, horizontal scaling, 12-factor apps, it's being rewritten by AI workloads. And what's fascinating is that it's not a one-way street. AI is changing cloud-native, but cloud-native is also enabling AI to scale in ways that weren't possible before.
But aren't we just talking about running ML models in containers? I mean, we've been doing that for years.
No, it goes way deeper than that. We're seeing AI actually influence the control plane itself. Think about it. Kubernetes makes scheduling decisions, right? Well, now we have AI models that are learning from historical scheduling patterns and making predictions about future resource needs. It's meta in the best way possible.
So you're saying AI is eating its own dog food, using intelligence to manage intelligent workloads?
Exactly. And here's what's really interesting for platform engineers. This isn't just about efficiency gains. We're talking about a fundamental shift in how we approach reliability, security, and even developer experience. The numbers are compelling, too. Organizations using AI-enhanced cloud-native platforms are seeing 40 to 60% reductions in resource waste.
But wait, doesn't this create a whole new set of complexities? I mean, debugging a traditional autoscaler is one thing, but debugging an AI-driven scheduler sounds like a nightmare.
And that's the crux of it. We're at this inflection point where the benefits are clear, but the operational model is still being figured out. Platform teams need to evolve from being infrastructure operators to becoming AI infrastructure orchestrators. It's a completely different skill set.
Okay, so where does this leave us as platform engineers? Are we all supposed to become ML experts now?
That's the million-dollar question, and it leads us right into the heart of this transformation.
All right, so let's dig into the technical meat here. When you say AI is transforming cloud-native workloads, what does that actually look like in practice?
Let me give you a concrete example. Take Netflix's recent implementation of their AI-driven traffic management system. They're processing over 150 billion events per day, and traditional rule-based autoscaling was leaving them with either over-provisioned clusters or degraded performance during traffic spikes. They implemented a predictive scaling system using time series forecasting models that analyze not just current load, but also historical patterns, content release schedules, and even social media sentiment.
That's impressive, but what kind of accuracy are we talking about?
Their prediction accuracy for traffic spikes improved from 65% with rule-based systems to over 92% with AI-driven predictions. But here's the kicker. The real win wasn't just in scaling up, it was in scaling down. They reduced their baseline resource allocation by 35% because the AI could confidently predict quiet periods.
But doesn't training and running these AI models consume resources themselves? What's the net benefit?
Great question. The overhead is real. They're dedicating about 3 to 5% of their compute resources to running these optimization models. But when you're saving 35% on baseline resources and preventing outages that could cost millions in lost revenue, the math works out. Plus, they're using techniques like model distillation to create lighter weight inference models that run at the edge.
Speaking of edge, how does this play out in edge computing scenarios?
This is where it gets really interesting. AI workloads at the edge have completely different constraints: limited compute, intermittent connectivity, strict latency requirements. Cloud-native principles like containerization and declarative configuration become even more critical. We're seeing patterns emerge like federated learning, where models are trained across distributed edge nodes without centralizing the data.
That sounds like an operational nightmare. How do you even monitor and debug a system like that?
You're absolutely right to be concerned. Traditional observability tools fall short here. That's why we're seeing a new generation of AI-native observability platforms. Take Datadog's new ML Insights feature or New Relic's AI Ops capabilities. They're using anomaly detection not just on metrics, but on the relationships between metrics. They can identify when an AI model's behavior is drifting before it impacts performance.
Can you give me a specific example of how this works?
Sure. Let's say you have a recommendation model running in production. Traditional monitoring might alert you when latency spikes or error rates increase. But AI native monitoring can detect when the model's prediction distribution starts shifting. Maybe users are getting less diverse recommendations. It correlates this with upstream data pipeline changes, identifies the root cause, and can even trigger automated rollbacks.
That's powerful. But what about the resource allocation? GPUs aren't cheap.
This is where Kubernetes really shines. The latest versions have native support for heterogeneous resources, GPUs, TPUs, even custom accelerators. But it's not just about scheduling. Projects like NVIDIA's GPU Operator are making it possible to dynamically provision GPU resources, share them across workloads, and even implement GPU virtualization. We're seeing utilization rates jump from 30 to 40% to over 80% with intelligent scheduling.
Those are impressive numbers. But what about the cold start problem? AI models can be huge.
Model serving is definitely a challenge. That's why we're seeing innovations like model caching layers, lazy loading, and even predictive model preloading based on request patterns. Selden Core, for example, implements a multi-level caching strategy that keeps frequently used models warm while efficiently managing memory.
This all sounds great for large organizations, but what about smaller teams? Is this complexity manageable?
That's where the cloud-native ecosystem really delivers. Managed services like Amazon SageMaker, Google Vertex AI, and Azure ML are abstracting away much of this complexity while still leveraging cloud-native principles under the hood.
So we've covered a lot of ground here. For platform engineers listening to this, what are the practical takeaways? Where should they start?
First and foremost, don't try to boil the ocean. Start with observability. Before you can optimize with AI, you need to understand your current workload patterns. Implement comprehensive metrics collection, not just resource utilization, but also application-level metrics, user behavior patterns, and business KPIs.
Any specific tools you'd recommend?
For teams just starting out, I'd suggest looking at open source solutions like Prometheus with Thanos for long-term storage, combined with Grafana for visualization. But here's the key. Start collecting and storing this data now, even if you're not ready to implement AI-driven optimization. You'll need historical data to train any meaningful models.
That makes sense. What about the skills gap? Should platform engineers be learning PyTorch and TensorFlow?
Not necessarily. The more important skill is understanding AI workload characteristics. Learn about batch versus online inference. Understand GPU memory patterns. Get familiar with concepts like model versioning and A/B testing for ML. You don't need to be a data scientist, but you do need to speak their language.
What about organizational changes? This seems like it would require different team structures.
Absolutely. The most successful organizations I've seen are creating hybrid roles, ML platform engineers who sit at the intersection of data science and platform engineering. They understand both worlds and can build bridges. Start by embedding platform engineers in data science teams and vice versa.
But what about the risks? We're essentially giving AI control over critical infrastructure decisions.
That's a crucial point. Always maintain human oversight and implement gradual rollouts. Start with AI as an advisor, let it make recommendations, but require human approval. Use techniques like shadow mode, where AI decisions run in parallel with traditional systems. Only after you've built confidence should you move to automated execution.
Looking ahead, what should platform engineers be preparing for?
Three big trends. First, AI-specific hardware is evolving rapidly. We'll see more specialized accelerators beyond just GPUs. Second, edge AI is going to explode. Think about preparing for scenarios where you're managing thousands of small models at the edge rather than a few large models in the cloud. Third, regulatory compliance for AI is coming. Start thinking about model governance, explainability, and audit trails now.
That sounds like a lot of additional complexity. Is it worth it?
Here's how I think about it. Cloud-native technologies democratized scalable infrastructure. AI is now democratizing intelligence. The combination is powerful, but complex. The organizations that figure this out will have a massive competitive advantage. We're talking about systems that not only scale automatically, but learn and improve over time.
So it's not just about running AI workloads on Kubernetes, it's about creating intelligent infrastructure.
Exactly. And here's my parting thought. We're moving from infrastructure as code to infrastructure as intelligence. The platforms we build won't just execute our instructions, they'll anticipate needs, optimize themselves, and even heal autonomously. It's not science fiction anymore. It's happening now.
That's both exciting and a little scary.
It should be both. The key is to approach it methodically. Start small, measure everything, and always maintain the ability to understand and override AI decisions. The future of platform engineering isn't about choosing between human expertise and artificial intelligence. It's about combining them in ways that amplify both. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
Until next time.